this is for the lesson for anyone who missed it. We started off with atomic physics, so let's start right at the beginning. Everything's made of protons. Let me choose the right pen. Protons, positive, neutrons, neutral, electrons, negative. No prizes for guessing how they're arranged. Been doing this for quite a long time. Protons, neutrons in the nucleus, and around the outside we have the electrons. And it's worked pretty well. Got 118 elements. Everything that we know is made of stuff is made of these three particles, and they form themselves into the periodic table quite nicely. However, by the 70s we were starting to realise that the proton and the neutron were not everything, and this video is concerned with what they're made of. But before we get there, let's just have a quick recap on how we name stuff. So we take an element X and we need to name the mass at the top, and by the mass we mean the number of neutrons plus the number of protons, stuff in the middle as I like to technically call it, and stuff at the bottom we have the proton number, or the atomic number as it's called. Proton, not proton. And it's this number here that tells you what element you've got. So we look across the periodic table, tick, 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 and you go up by one proton each time. However, we're scientists, so we start messing around with the nuclei. And what we figured out is that we could take neutrons, put them on, and we could take neutrons off. And we do this quite regularly, particularly in hospitals. We bombard elements to turn them into isotopes, and I'll show you why we do that in a minute. So let's take an example. Let's take hydrogen 1,1. One proton, one electron around the outside, keep it neutral. However, we can have an isotope called hydrogen 2,1, where what we've done is we've bolted on an extra neutron to the proton. And chemically, no different. Behaves exactly like hydrogen normally does. Has one electron, it's quite happy. We call this deuterium, de meaning two. And 3, 1, hydrogen. This is called tritium. And again, we've just bolted in another neutron. So there we go, and a proton there. So these are isotopes, neutrons being added or removed. Now, why would you want to do that? Well, it turns out that the periodic table is actually a snapshot of their elements in their best. If we move across to what they really look like, we see none of those. Let me just drop out of this. We see that actually elements look like this. Across the bottom we've got Z, up the side we've got N, I think. There we go. So, take hydrogen. Hydrogen 1,1, there's our first one. That is normal, happy, stable hydrogen. 2,1, an isotope, 3,1. But you can keep going. If we turn on the legend, you see that by the time it goes 5,1, 4 extra neutrons, that you've got something with a half-life of less than a trillion seconds. So it can exist, but nature doesn't let it exist for long. And we can move along these purple lines. We see there lithium 7,3, very stable, so 6,3. However, if you put an extra neutron on, or you have a neutron missing, immediately this thing starts falling to pieces. And the same's true for a lot of the elements. We can move on up. Oxygen 16,8, but in rare cases 17 and 18. But move along, get to the isotopes, and immediately they all start falling to pieces pretty quick. And so that purple line is the one that makes it onto the periodic table. The most abundant version of each one, so sodium 20, sodium 23, neon, sodium, magnesium. They make it to the periodic table, but the others all exist, and there are a lot. And humankind has been messing around, creating these isotopes in laboratories, finding rare examples of them, and in some cases using them for medical uses. So, why might we want to do it? Well, first of all, we'll go over to what protons and neutrons are made of. In the 70s, we started smashing atoms together really well. And what we discovered was that a proton is in fact made of 3 subparticles called quarks. They exist in 3 different colours, red, green and blue. But they are not colours as we would experience them. We needed a way of kind of describing the bonding, and so we used the idea of colour, because the 3 primary colours of light add together to give white. So we always say quarks bond to form white. Now these quarks are fluctuating between their colour all the time. However, the others two change correspondingly to fit. So you always get white. In terms of charge and mass, well, if 3 make a proton and we call the proton a mass of 1, then 3 quarks is a third, and a third. So each one has a charge as a mass of a third, and we can get 2 flavours of quark. We can have up and we can have down. And again, these are not as we experience things being up or down. It's just a quantum number that allows you to explain why things happen. So let's take a proton, positive. We end up with up, up, down. And if we look at the charge, we can see that it does match this positive. Ups are plus 2/3, plus 2/3, and the down is minus a third. You really do have to know that. And if we add 2/3 together, we get 4/3. If we take away a third, we end up with 3/3, which is 1. So it works. Tick. Have a go at neutrons. Neutrons are down, down, up, right underneath the charge of each of the quarks. Prove that it is indeed 0 charge. Next, messing around with those isotopes, making them unstable, causes decay. And atoms do not like energy. As soon as you look at, why is anything happening? Why do balls fall? They want to get rid of GPE. Why do hot drinks get cool? They want to get rid of thermal. All chemical reactions happen to become in lower energy states. And the nuclei is no different. If we hop across to this piece of software here, we can build ourselves an atom. Here we've got simple hydrogen. We can add a neutron, we make an isotope, deuterium. Add another a neutron, we have an isotope 3,1. And you see already it's becoming unstable. And eventually it decays, gets rid of the neutron. And we can go through and we can build another one. And again it's unstable, beryllium, lithium. Back to helium, and now it's happy. And so if we mess around, if we have an unstable amount of neutrons to protons, we create something that's radioactive. Now nature has quite a few ways of getting rid of that energy, as you're seeing in front of you, and we're going to talk about those different modes of decay. Now 3 of them you've heard of: alpha, beta, gamma. Quick reminder, alpha is a mass of 4 and a charge of plus 2, and the reason being it's made of 2 protons, 2 neutrons. Let's get rid of those. It's actually a helium ion. So there we go, plus, neutral, not perfect, but it'll do. You've had a look at that before in P2. The beta is an electron, and that electron is coming out of the nucleus. And we'll talk a bit about why it does that in a minute. It has a charge of -1 because it's an electron. And gamma rays, well, they're EM waves. They're nature's way of packaging light up, of energy up, and thrown across the universe and transferring energy. And it has a charge of 0. However, there are 2 more that we're going to learn about in Wednesday's lesson. We are going to do about positrons. That's not that way. It is wave 0. A positron is a beta plus. So now I'm going to start writing beta minus for electron beta decay. A positron, which is beta decay, it is a positron, and this is an antimatter electron. And for a lot of people that's news, because they didn't realise that actually antimatter was real. It wasn't just something in the films. It has a charge of +1. It's exactly the opposite of an electron. And the other form of decay, less exciting, is neutron decay, where literally it just kicks out a neutron. Doesn't need saying about what the structure is. And charge, no cigars for guessing 0. So, let's have a look. You'll be familiar with this. We did an experiment while you guys were away. We took an alpha emitter, went about 3 centimeters in the air, and it hit paper and it stopped. We had beta decay, and let's do beta minus. It got through the paper, because the paper's really empty looking to the beta. However, by the time it hit the metallic lattice structure of aluminium, it got stopped. And gamma. Well, to gamma, everything looks like a cloud. Doesn't matter how solid it looks. It's just like going through a plane in a cloud. And it'll get all the way through, and it's until you get to lead, which is particularly dense, that it starts to make a dent. And even then, some will still get through. And you can never truly stop gamma. There's billions of them going through you now. Most of them have come from the edge of the universe. So, don't worry too much about it. Those are alpha, beta, gamma. Now, we did try a new detector today, which was quite handy, and we used what was called a 2D spark gap, can't spell, detector. Pretty funky little machine. Take a bar of metal, charge it to 5,000 volts, 5 kilovolts, have some oxygen behind it, have the air available to it, have a plate behind it, which is at 0, and if you put some ionized gas in the air here, that was supposed to be that, if you put some ionization here, then you'll get a bolt of lightning moving from one end to the back. Get a spark. So how do we ionize the air in between? We introduced alphas. Alphas come along with their +2 charge. They go across and in, and they rip off electrons from the oxygen and the nitrogen in the air in between the two plates, and that caused the air to move. It broke down the resistance, and you got a spark. So it's quite funky. You can connect it to a PC, and you can record the distance between the two and the amount of charge you get, number of counts per second, and you realise that the absorption, if here is 0, you're next to it, it's really high, and the further away you move, it drops off as 1/x squared. And I've got a little video, I'm going to try and play it, probably will crash, but let's give it a go.